Okay, let's just jump right in. We're constantly talking about the global tech race, right? AI, new phones, all of it.
Right, the cutting edge.
But what if I told you almost every single piece of that advanced tech funnels back to a single kind of secret industrial bottleneck?
And it's not in Silicon Valley, it's not in Asia, it's in a small town in the Netherlands called Veldhoven.
Exactly. That bottleneck is a company called ASML Holding. And our deep dive today is into how this one company became the absolute non-negotiable gatekeeper for our entire digital future.
They hold a 100% monopoly on the machines that make the world's most advanced chips. These are called extreme ultraviolet or EUV lithography systems.
We've gone through the research on ASML's, 30-year journey, the mind-bending complexity of these machines, and their role at the center of this geopolitical tech race.
So our mission is to show you why ASML isn't just a tech company. It's probably the most critical choke point on Earth, and its output really does dictate the future for all of us.
Let's start with that number you mentioned, because it's just wild. 100%. You just don't see that in high tech.
You really don't. It's a total monopoly. To get why that's so powerful, you have to understand what lithography is. Think of it as the printing press for computer chips.
So it's etching all the tiny patterns onto the silicon.
Exactly. And for decades, we used something called deep ultraviolet light, DUV. It worked great.
But then it stopped working great. Why the switch?
They hit a wall, a literal physical wall. DUV light has a wavelength that's just too long.
Too blunt of an instrument.
Precisely. If you want to keep Moore's law going, if you want to make the chips in today's iPhones or AI servers, we're talking 5 nanometer, 3 nanometer chips, you have to use the much shorter wavelength of EUV light.
And ASML is the only company in the world that sells the machines that can do that.
The only one, which creates this intense concentration. I mean, who can even buy these things?
Our research shows it's just 5 companies operating EUV at high volume. You've got TSMC, Samsung, Intel, SK Hynix, and Micron. That's it.
That is a tiny customer base for such a critical technology.
It's a huge strategic vulnerability.
Mm-hmm.
And it leads to maybe the most important number in this whole story.
0.
0 EUV machines have ever been shipped to China.
Not a single one. And that, right there, is the foundation of the modern tech war. The U.S. and its allies are using this one Dutch company as the ultimate choke point.
And financially, you can imagine what this means. ASML is now Europe's biggest tech company by valuation. They have a backlog of orders worth, 36 billion euros?
Yeah, a 36 billion euro backlog. It means they know what their revenue will be years in advance. They are totally insulated from the market. They're not a participant. They are the infrastructure.
Okay, so they're indispensable. But the machines themselves, the engineering is on another level. I mean, the next-gen ones cost close to $400 million a piece.
And the scale is hard to comprehend.
Mm-hmm.
A single machine, one EUV system, weighs between 180 and 200 tons.
200 tons.
Just to ship one of them, you need 3 Boeing 747s.
3 jumbo jets.
Yeah.
For one machine.
Or 40 freight containers. And when it arrives, it's not plug and play. It's a construction project.
Right. It takes a team of 250 engineers, 6 months, just to put it together.
And calibrate it. Over 100,000 parts, 2 kilometers of cables. But the real magic, the insane part, is the physics.
How they actually generate that special EUV light.
You're basically building a tiny star inside a vacuum chamber.
A star in a box.
Pretty much. Because EUV light doesn't really exist in nature, and glass absorbs it, so you can't use lenses. You have to invent a whole new way of doing things.
And the solution they came up with is called the tin droplet dance. Can you walk us through that? It sounds like science fiction.
It really does. Imagine high-tech clay pigeon shooting, but you're doing it 50,000 times a second.
50,000 per second.
They shoot a microscopic droplet of molten tin into a vacuum chamber. It's moving at 70 meters per second.
Okay.
Then a super powerful CO2 laser hits it twice. The first pulse flattens the droplet. The second one vaporizes it instantly into plasma.
And that plasma is what creates the light. How hot does it get?
It gets heated to 500,000 Kelvin.
Wait, say that again?
500,000 Kelvin. For context, that is hotter than the surface of the sun. Only at that temperature does the plasma glow at the exact 13.5 nanometer wavelength they need.
Unbelievable. And since you can't use lenses, you need mirrors. Mirrors developed by ZEISS in Germany. And the precision there is just legendary.
It's the most precise manufacturing on Earth. The light has to bounce off 11 different mirrors inside this perfect vacuum to reach the silicon wafer.
And the analogy from the source material for their smoothness is just perfect.
It really is. It says if you scaled one of these mirrors up to the size of Germany,
The entire country of Germany.
the largest bump on that entire surface would be just 1/10 of a millimeter high.
That's essentially flawless. But even with that perfection, after bouncing 11 times, how much of that star-hot light actually makes it to the chip?
Almost none of it. That's the crazy part. Even with superhuman precision, you lose energy at every reflection. By the end, less than 2% of the original light energy hits the wafer.
Wow. So all that complexity, all that heat, for just 2% efficiency.
And that tells you everything you need to know about why this was so hard to figure out.
Which brings us to the obvious question. Why can't anyone else do this? If it's this valuable, why hasn't a competitor just copied it?
Because you can't. It wasn't a quick project. It was a 30-year, multi-billion-dollar scientific siege. We're talking $15 to $20 billion in total investment.
ASML alone spent over 6 billion euros just on R&D. But even they couldn't do it alone, right?
No, it was such a huge gamble that their biggest customers, Intel, TSMC, Samsung, they actually had to chip in. Back in 2012, they invested billions directly into ASML's R&D.
So they funded their own monopoly supplier.
Because the alternative was the end of Moore's Law. It was this or nothing.
And today that technological moat is defended by, what, over 33,000 patents? But the real barrier is the supply chain.
That's the unreplicable part. People call it the critical triad. You have ASML integrating the system, but they rely on two German companies they can't replace.
First is ZEISS, for those insane mirrors we just talked about. ASML had to buy a chunk of ZEISS just to lock that relationship down.
And the second is a company called Trumpf. They make the incredibly powerful CO2 lasers. These are the most powerful lasers of their kind ever built for production.
These are not parts you can just order from a catalog.
Not at all. There was a quote from Trump's CTO that said it all. He said, "If we fail, Moore's Law will discontinue."
Wow, so that's the real gatekeeper. It's not just one company's patents, it's this decades-long, interwoven partnership.
Exactly. And we know it's impossible to copy because people have tried. ASML's former CEO said competitors who tried to reverse engineer the machines just failed. They ended up breaking them during disassembly.
Because they just didn't have the deep institutional knowledge.
You can't just take it apart and see how it works. It's too complex.
And that industrial power inevitably makes ASML a geopolitical weapon. Let's talk about the blockade, the moment this all became official policy.
It all came to a head in 2019. ASML was all set to ship its first EUV system to China's biggest chipmaker, Pennac.
But the U.S. government was not happy about that.
Not happy at all. They were worried about military applications, and the diplomatic pressure was intense. Reports say that the U.S. Secretary of State at the time, Mike Pompeo, personally called the Dutch Prime Minister.
A phone call between national leaders over one piece of industrial equipment. That says it all.
And the Dutch government pulled the export license. The machine never shipped. Since then, the restrictions have only gotten tighter, now covering some of the less advanced DUV machines, too.
So China's response was to try and find a workaround, right?
Yeah.
Using the older DUV tech.
A brute force approach. A company like SIMAC used its DUV tools with a technique called multi-patterning.
Which means what, exactly?
It means you expose the same chip multiple times 3, maybe 4 passes to etch the tiny features you'd normally do in one pass with EUV. Yeah. And they actually managed to make a 7-nanometer chip this way.
That's pretty impressive, technically. But what's the catch? Why isn't that a sustainable solution?
The catch is cost and reliability. Every time you re-expose the wafer, you risk creating a defect. You risk misalignment. And the data we have on this is pretty damning.
How bad are we talking?
The reported yields for SMIC's 7-nanometer chips were somewhere between 15 and 33%.
So potentially 2/3 of the chips on every wafer were just duds.
Or more. And the cost was estimated to be 50% higher than what TSMC could do with EUV. It's just not viable for mass production, and it probably hits a hard wall at 5 nanometers.
We did see reports in 2024 about a Chinese EUV prototype, but it hasn't made a working chip yet. So what's the consensus on the real technology gap?
Most experts, even the leadership at ASML, they all say the same thing. China is likely 10 to 15 years behind in developing a reliable mass production EUV machine. The blockade is working.
Okay, this brings us to the final and maybe the most tense part of this story. These machines aren't just tools. They're strategic assets with a kill switch.
That's exactly right. The reporting on this was fascinating. The idea is that ASML and TSMC have the technical ability to remotely disable every single EUV machine in Taiwan if China were to invade.
So this goes way beyond an economic choke point. This is an active military deterrent.
A huge one. The reports claim the Dutch government even ran simulations of an invasion scenario, and that ASML confirmed to them this capability was in place.
How would that even work? How do you remotely brick a 200-ton machine?
Well, these machines are not standalone. They're constantly connected back to ASML servers. They need constant software updates, telemetry handshakes, specialized maintenance.
So you cut that connection, or ASML sends a command.
And it becomes a 180-ton paperweight. Without the proprietary software and the on-site engineers who are required to keep them running, they would just stop working.
Has anyone officially confirmed this? ASML? TSMC?
No. Official silence. Nobody will confirm or deny it, which in a way makes the deterrent even more potent. It just hangs out there unresolved.
And while all this geopolitical tension is swirling, ASML is already moving on to the next generation. High-NA EUV.
High NA. It's even bigger, even more complex. It costs up to $380 million for one machine,
380 million.
but it offers much higher resolution. And interestingly, Intel has been the big first adopter here. They got the very first one trying to leapfrog PSMC and Samsung.
While TSMC is being a bit more cautious, it seems.
Yeah, they're trying to squeeze more out of the current generation before paying that huge sticker price. But the tech never stops.
So wrapping this all up, what does this mean for you, the person listening to this?
It means the engine of the entire AI boom, the key to every powerful computer on the planet, is completely dependent on this one company in one industrial park.
Built on 30 years of research in this unique, irreplaceable global partnership.
And it means supply chain security isn't some abstract concept. It is the physical location of these 200-ton machines. ASML's shipping schedule directly impacts your phone's performance and, frankly, global military power.
The next time you hear about the chip war, remember it's really about whether one company in a small Dutch town controls the future of computing. And right now the answer is yes.